Hey everyone, in this video we're going to go over the concept of indefinite integrals, and we'll also do some definite ones, and we're just going to do a bunch of examples just to get really familiar with how to find definite and indefinite integrals. So first, the properties. So the properties of indefinite integrals, and actually the first two also work for definite integrals. So if you have a constant, the integral of a constant times a function, you can take the constant out of the integral and then just integrate that. So for example, if I had something like the integral of 3x squared dx, right, what the property then says is I can take the 3 out and then just say the integral of x squared dx. And now I can use the general power rule here. And so this will just be x cubed over 3 plus c. And then my 3's will cancel. So that is how we can apply a constant. The second one is if you have the sum or difference of two functions and you're trying to find the antiderivative, the integral of that, then you can find the derivative of each piece, the antiderivative of each piece. So for example, if I had something like x squared plus e to the x, right? These are two functions. And so I can say this is really the integral of x squared plus the integral of e to the x dx. So we tend to do that in our heads anyway, but that is the actual property. And all these properties come from the Riemann sums. Remember that an integral is a Riemann sum. So when I see the integral represented for a definite integral here, like this last one, when you have a definite integral on the interval ab, then in this case the integral from b to a, so the interval is a to b, but this says b to a, then it's the negative of ab. And the reason being is that our delta x, usually we say is b minus a over n, so in this case it will be the top limit minus the bottom limit, so this will be a minus b over n. But to make it look like our usual delta x, we can factor out a negative, and now you have b minus a over n, which is negative delta x. So you will have the negative out front when you do a Riemann sum. And so all of these properties really come from the properties of summations. So let's try an example. So find the following integrals. Here we have part A plus 2 root x dx. Now remember that the dx is, here we're trying to find the antiderivative. So that means that this a plus 2 root x is the derivative of something, and the derivative is taken with respect to x. So with respect to the variable x. So as I change the variable, just pay attention to what this is. So because this is telling us that x is the variable, so let's rewrite this. So I can say this is the integral of 8 plus 2x to the 1/2 dx. And so here it's really the second property. I have 8 plus 2 root x, so I can split them up if I wanted to, or you can just do it all in a single line. But really, without writing the steps, that's really what we're doing. We're splitting up the integral. So this will be then just 8x plus, and then the antiderivative of this, we can use the general power rule. So add 1 to the exponent. I'm going to have x to the 1/2 plus 1, which is 3/2, and divide by that new exponent, divided by 3/2, and then plus a constant. Don't forget your plus c when you have an indefinite integral. So then this simplified becomes, what is this? Dividing by a fraction is the same thing as multiplying by the reciprocal. So you're really multiplying by 2/3. That becomes 4/3 x to the 3/2 plus c. Our next example, let's look at this. Be e to the x plus 1 over the square root of 1 minus x squared. So hopefully we recognize this as some antiderivatives already. If you don't, it might be worthwhile to go back and look at the table of derivatives so that we can recognize this as the derivative of something. And so here we recognize this, the antiderivative e to the x is e to the x, and recognize this as the derivative of inverse sine. So that means that is the antiderivative, 1 over the square root of 1 minus x squared, is sine inverse of x. And then plus c. You could also write this using the arc notation, so we could say plus arc sine of x plus c. Now our third example here, see the integral of the square root of t times t minus 1 dt. So here I am changing the variable, right? So it's dt. So that means that this is the derivative of something, and the derivative was taken with respect to the variable t. Now here there's something to watch out for. This is not a property of integrals, right? If I have the integral of f of x times g of x dx, this does not equal the integral of f of x times the integral of g of x. So you cannot integrate piece by piece. Just like in derivatives, you couldn't take the derivative of a product piece by piece. We had the product rule. So here with integrals, you can't just integrate the first and then integrate the second. So what we have to do is rewrite and multiply it out. So I'm going to rewrite this integral as distribute the square root inside. So this is t to the 1/2 here distributed in. So this is t to the 3/2. I'm not taking the derivative, right? I'm just distributing minus t to the 1/2. Or not the derivative, the antiderivative. So now, remember the integral, this summa notation, tells us to take the antiderivative. We don't have limits of integration, so we're not being asked for an area, but we're being asked for the antiderivative. So now let's use the general power rule to take the antiderivative here. So this will be add 1, so it'll be t to the 5/2 divided by 5/2, that's the same thing as multiplying by 2/5, minus t to the 3/2, right? Add 1, divide by 3/2, which is the same thing as multiplying by 2/3, and then plus c. So the big thing here is to remember that when you have the product of two functions and you want to find the antiderivative, you can't just do the antiderivative of the product. So be careful about that. Make sure that you distribute it through, or when you get to Calc 2, you'll learn a lot more techniques of integration and how to undo products, how to undo quotients, how to undo the chain rule, and so on. So let's look at part D. All right, so we have another, it's not an x anymore, and this is just, we have to get used to working with different variables. As long as I have the same variable here and then d theta, well, actually you don't have to have the same variable, but this d theta tells you you're taking the antiderivative with respect to that variable. So even if I had something like x and then cosine theta d theta, right, then this tells me, well, this is the derivative of something with respect to theta. So that means that x is a constant and the variable is theta. So this will just be antiderivative. This will be x, and the antiderivative of cosine is sine of theta plus c. So that will be the antiderivative of this, because this part is really important. This is what tells me that this was the derivative of some function, and the derivative was taken respect to the variable theta, which means that even though here x appears like it's a variable, it's not. I can consider it a constant. Well, it might be a variable, but it's not the one that we're concerned with. Here, everything is in terms of theta, so we're good, but we run into the issue that, oh, I have a product, so I can't just integrate piece by piece. So let's distribute. So let's rewrite before we find the antiderivative. So this will be the integral of secant times secant is secant squared theta plus secant times tangent is secant theta tangent theta d theta. And do we recognize those antiderivatives? Yes. The antiderivative of secant squared is tangent. Check it, right? What's the derivative of tangent? The derivative of tangent is secant squared. And what about the antiderivative of secant tangent? That would be just secant theta. And so this is our antiderivative plus a constant. Don't forget the plus c if you have an indefinite integral. Again, indefinite means you have no limits of integration. So when you have an indefinite integral, it's just asking you for the antiderivative. Now part D, part E, is a definite integral. So that one will be asking us for the area between the curve and the x-axis. And now, because we have the beautiful thing that is the fundamental theorem of calculus, we do not have to sketch this curve and try to figure out what it looks like and draw rectangles do a Riemann sum, we can be done with that phase of this chapter and say like, oh, thank goodness for the fundamental theorem of calculus, because this just tells me that this is going to be f of 2 minus f of 1, right, where f, capital F, is the antiderivative. So the fundamental the antiderivative of the function little f of x. So let me call this little f of x instead of writing out the whole thing. So I hope that you're able to see why the fundamental theorem of calculus is so valuable and useful, is because now I can just really find any integral, the area under any curve, because of the niceness of the fundamental theorem of calculus. All right, but now how do we integrate this? So I have sine, the arguments are different. So I have sine of 2x over sine of x. And so I can't just say, oh, cancel out the x's, right? This is a function in itself, sine of 2x divided by another function, sine of x. But here we can use the identity. The sine of 2x is equal to 2 sine x cosine x. So we can replace that. So let's rewrite it, this integral, as the integral from 1 to 2 of sine of 2x. So we're going to replace that using this identity. 2 sine x cosine x divided by sine x. And then plus the 3 to the x stays. There's no need to rewrite that one. So always ask yourself, do I need to rewrite my function before I integrate? And now here we can see that I can say sine x divided by sine x is 1. So I'm just left with the integral from 1 to 2 of 2 cosine x plus 3 to the x dx. So now this is simplified. And now I'm ready to take the antiderivative. So the antiderivative of cosine is, what's that? That'll be 2 sine x. And let's check it. The derivative of sine is positive cosine, so we're good. Plus the antiderivative of 3 to the x. So that'll be 3 to the x divided by the natural log of 3. This is a definite integral, so I don't need the plus c. So I can say I'm going to evaluate this from the lower limit of 1 to the upper limit of 2. And now we can plug in your, starting with the top limit, always do top limit minus bottom limit. So this will be 2 sine of 2 plus 3 squared over natural log of 3. And then minus, make use of parentheses here, 2 sine of 1 plus 3 to the 1, so just 3 over the natural log of 3. And so this will be as far as we can go. Well, actually, we can sine of, this is assumed we're in radians, right? So sine of 2 radians, which is, so this is not one of those nice angles that we can find. So like if it was pi over 6, I can find what pi over 6 is. If it was 0, I can find what sine of 0 is. Pi and all of those nice reference angles, right? Pi is what, 3.14 radians. Pi over 2 is half of that. So this is 2 radians. So in between pi over 2 and pi. But here we can say 9 over natural log of 3 minus 2 sine of 1 radian, and then distribute the minus, minus 3 over ln of 3. These are like terms, 9 over ln of 3 and 3 over ln of 3, so we can simplify those. So I'm going to have 2 sine of 2 radians minus 2 sine of 1 radian, and then 3 or 9 ln of 3 minus 3 ln of 3 will be plus 6 over natural log of 3. And that will be our answer. Okay, so this, in this case, we're finding the area between this curve and the x-axis on the interval from 1 to 2. And our last example, part F, is again a definite integral. So, and now our variable is u. So this is the variable, and this is the antiderivative. We're going to find the antiderivative, thinking that this is the derivative of something and it was taken with respect to the variable u. So we're going to make use of our fundamental theorem of calculus again, instead of having to do a Riemann sum. So it'll be the antiderivative evaluated at 1 minus the antiderivative evaluated at -1. But I have a product again, so let's be careful. You can't just integrate piece by piece, so we have to multiply it out. So let's rewrite. So I'm going to have the integral of -1 to 1 of u, I have 1 minus u quantity squared, so we have to square the u minus 1 first, right? I can't bring this u inside. Order of operations tells me I have to do exponents first, and then we can do that multiplication. So this will be u times, let's square this out, so it'll be 1 minus 2u plus u squared du. And now we can bring this u inside that parentheses. So I'm going to have the integral from -1 to 1 of u minus 2u squared plus u cubed du. And now I can take the antiderivative and then apply the fundamental theorem of calculus. So this will be u squared over 2 minus 2/3 u cubed plus 1/4 u to the 4th. No need to do plus c because this is a definite integral. If you did plus c, what you will find is that once you plug in your top limit and your bottom limit, the c's will cancel. So plug in 1 and -1, so you're going to have 1/2 minus 2/3 plus 1/4 minus, and when you plug in the bottom limit, always make sure that you put parentheses. You don't want to forget to distribute the negative. So -1 squared, that's 1, so 1/2, and then that -1 cube is -1. So I'm going to have -1 cubed, which is -1 times a -2, so it'll be plus 2/3, and then -1 to the 4th is +1, so plus 1/4. And now distribute that negative. And combine like terms, but notice that here the 1/2 minus 1/2 cancels, the 1/4 minus 1/4 cancels, so I'm left with minus 2/3 minus 2/3, so that will be a plus 4/3, or I mean a -4/3. So that will be my area between the curve and the x-axis. And I know what you're thinking, what, Nate, you said area and it's negative? We will learn in the next video about net area. So what the negative is telling me is essentially that most of the area lies underneath the x-axis. So just to give you a preview of what the next video will entail is essentially what's happening here is that if I have my function and I have, what was it, between -1 and 1. So what could be happening here is that maybe most of the area is underneath the x-axis, right? So when I do then the net area, I'm going to have, is going to be negative, because the negative, it's not that the area is negative, it's just that what it's telling me is that most of the area lies under the x-axis. So that might be what's going on here. So that's what we're going to be looking at in the next section, which is net area. So here, we expect it to be negative in this particular example. All right, email me if you have any questions.